Hello and welcome everyone to this one-of-a-kind gathering for what is quite frankly a one-of-a-kind book, I think. Welcome especially to this absolutely awesome galaxy of educators who have collaborated on this book project. I urge everyone to check out their bios in the book or online to get a sense for their outstanding work in the field of computer science education. We will hear firsthand from many of them today. And I have to say that this book really reflects this. It speaks to the spirit of collaboration in this amazing computer science education community. So this handbook has been created primarily with teachers in mind to help them understand what teaching intro programming is all about. And we tried very hard to stay true to these adjectives that we have put in here that we share very often, and I think it's on the back of the book as well, and produce a resource that bridges what we know from years of classroom practice and research to date to actionable ideas for the classroom. And in case you've not had a chance to check out the book, one of the cool things, of course, about it is the A to Z organization of the 26 chapters. And we will hear about each of these chapters today, which is what is so great about this gathering. There's a foreword written by Mark Gusdale. It provides a very meaningful backdrop to this book. It talks about this moment that we're in and why teaching CS in schools is a challenge, and how this book brings together all that a CS teacher needs to know about teaching intro programming. And there's a preface, a rather long one, and I would recommend anybody and everybody reading this book to actually read that first, because it provides a lot of guidance on understanding the way this book is organized and what it's all about and how to use it. And it explains how this book aims to help build teacher pedagogical content knowledge, or PCK. And we discuss content and pedagogy, and we share what we know from research on aspects of learning various CS topics that students often find difficult. And it's very heartwarming to see tweets like this. This is from someone I don't know who tweeted this yesterday, saying that has somebody been hiding all the PCK materials for CS? And so since the book aimed to fill exactly that need, it was really nice to see this written yesterday. So the table of contents has the preface has an alternate table of contents, which, as you know from the color version of the book, it's color coded. The chapters are color coded by concept and practice and pedagogy. And so a teacher reading the book might decide to tackle the book by color. So there are a few chapters that have this overarching quality. I just want to call them out. They're sort of umbrella chapters in that they speak to a broader view of this enterprise than the other chapters. And these are the ones on programming languages, misconceptions, our learning goals, what we want students to take away from K-12 CS learning experience, and formative assessment. So with that, my 3-minute intro, I think, to this book is done. And if everybody is ready, we will jump into the chapters right away. It's fortuitous for us and for Intro CS and for this book that the word algorithm starts with the letter A, because it's indeed a very good place to start when we talk about introductory programming. This chapter shares the what of algorithms, how they're related to programming. It discusses abstraction, which is also a very key idea that also starts with A, and I had a bit of a tussle in my head what A should stand for in this book. And it describes algorithms as procedural abstractions and key ideas that are important for learners to understand, that there are multiple solutions and algorithms to a single problem, that there are certain characteristics of algorithms, and then there are several examples from everyday life and programming context. What makes these good examples? It shares concrete teaching ideas for various grade levels and approaches to tackling how to talk about this idea. For the high school level, we go into searching and sorting algorithms and briefly talk about limitations. And even though the chapter goes briefly into the idea of algorithmic efficiency, it stops short of big O analyses, which become more mathematical and are not really covered in a very deep way at the high school level, if at all. So among the many activities outlined in the chapter and approaches, one of them is to convert existing algorithms which are in pseudocode into code. And this is an activity that I did in middle school, and it was really successful. It was basically code a program in Scratch, which tells somebody if their birthday was a leap year. And I said, go to Wikipedia and get the pseudocode. And they had been shared, the students had learned the idea of pseudocode. So they felt really empowered that they could go, and Wikipedia actually talks about the pseudocode and the algorithm for how to calculate whether a number, to determine whether a year is a leap year. And this, of course, came at the end of talking about nested conditionals and even Boolean logic. And it very organically introduced the modulo operator in Scratch, etc. Speaking of pseudocode is actually a great seg to chapter 2, which is like a companion chapter to this one. And it talks about creating flowcharts and pseudocode as part of this key programming practice of algorithmic thinking and planning before programming.
Firstly, just to say, it's a real pleasure to collaborate with Shuchi on writing a couple of chapters. I think one of the real features of this book is just how much he's managed to weave all the chapters together. Although they are standalone, although they talk about different aspects, there's these little bits every now and again which make you go and think, oh, if I want to read a bit more about this, I'll go to the next chapter or here. And I think that's a really good, where you've got a really good editor, they really sort of make you do that. And that works really well for this book. So just to tell you a little bit about our chapter on planning, and what we have done here, okay, is to very much think about some of these things, the importance of good planning to a quality outcome in programming. We very much thought also, we've drawn on some research to think about the structure of planning. Okay, what do you really want to have in it? What's the sort of levels of this? And you can read the chapter to find out exactly what we think about that. We very much start looking at this very early on in education. What about if we're working with very young children? How do we get planning in and get them thinking about their programming? Okay, and then we work all the way up, looking at block-based programming and how we might plan for that. Planning for text-based programming. We very much recognize some of the steps that children have when they're working towards precision in their algorithms, and we look at what an algorithm is, how it's different from code, the sort of language we might use to express ourselves in algorithms, and some of the things like initialization and objects that are important as part of planning as well. We recognise that a lot of students don't particularly like planning. They don't find it, a massively important thing. And they often want to jump straight into code. But actually we know that good planning really does improve their outcomes. So how can we get that balance right between planning and programming? And that's definitely something we address in this chapter. And how do teachers model good planning? So these are just some of the things that we include in this chapter, and I think, well, personally, I'm really looking forward to reading all the other chapters over the summer holiday as well. I think there's going to be lots that I can learn from everybody else who's collaborated on this book.
The next chapter is Creative Coding by Miles Berry, who is out camping somewhere in the UK. And so I will play his video next.
There are 5 key aspects of creative coding. The first is that creative coding should literally involve creation. It should involve making something, ideally to show to other people. Seymour Pappert's great insight of constructionism, that you make something in your head by making something in the world. Creativity also ought to emphasise quality. There should be a sense of striving for excellence, perhaps even striving for perfection, of making the best thing that one possibly can. Creativity should also pay attention to originality, that when we're doing this in school there should be some element of the young person's own original thought, original ideas goes into whatever it is that they're making. Creativity also demands some fluency, some mastery of the particular technical tools. That it isn't enough just to make something, you have to be good at using the tools that you have, this emphasis on craftsmanship as part of the process. And we should recognise that creativity takes place within an ecosystem, within an environment, as part of a community. It's never the coder working in isolation. They're inspired by the ideas of others and they get feedback from their peers. Let me give you some examples of what this might look like from K all the way up to 12. Perhaps with very young children we might start with something like Scratch Junior, a tool that is so simple that even very young children can figure it out for themselves, can explore, can experiment and can make something. They start with telling their own stories, they start with their own ideas for what these lovely characters on the screen might do. We might then move on to something like Scratch, where we have a building block, a programming language of snapping things together in order to make code rather than merely to write code. The great thing about Scratch is not the building blocks, but the share button there as part of the interface. Scratch programming takes place within a community of remixing, being inspired by, of learning from other people's work. And then perhaps in high school we might start to explore text-based programming, perhaps initially with Turtle Graphics, but sooner or later perhaps using something like the amazing on-screen in-browser P5JS toolkit for creating digital art, in this case creating Turtle Graphics by first creating the turtle. There are concerns, there are issues. The emphasis sometimes focuses on the making rather than the learning. That is a challenge for us as educators. There's a danger that children emerge with misconceptions. I worry at times about the efficiency of the process, and sometimes children's, young people's ambition exceeds their capabilities, and that can be the cause of frustration. So I think the pragmatic teacher will balance carefully scaffolding the construction of concepts with providing time for young people to independently explore making things that apply those ideas.
As you're doing that, just want to first of all thank you for bringing all these people together and doing what you're doing for computer science education at a time that we all realize it is expanding in popularity. People are realizing the importance of it, and to provide this tool for the educational community is fantastic. In particular, our chapter is on data structures, and I was reflecting back to the late 1980s when I was working with a gentleman at Fermi National Accelerator Lab, Leo Michelati, who introduced me to a relatively new language at that time, C++. And as we were visualizing physics data, we were talking about and writing about this new language, and we were very surprised to find that there was no common terminology used for simple ideas like data types built into the language. And one author may say they were built-in types. Another would say they were primitive types. Another would say it was fundamental types. And we were kind of surprised that there was no commonality among the writers. So as Baker and I started to explore the literature on data structures, we were relatively surprised to say 30 years plus later, there are no real common standard definitions in the literature for data structures. So it's such an important topic, we felt it was necessary to try to extend and expand these understandings of data structures for the general education community, for people who are coming from other fields and just starting in computer science, to people who have worked for years and want to have more clarification of really what a data structure is. So we tried to outline this fact that data types in general are not just the data, but it's also the associated functionality. So we mentioned some common ideas in everyday life that can be connected to data structures or collections of variables, and the geometries associated with the relationships between those variables, and the related functionality, as you mentioned in your chapter, the algorithms associated with accessing, retrieving, manipulating that data. So that's what the chapter tries to do, is give people a better understanding of just what data structures are, specifically linking to, at the high school level, the AP courses and what data structures students would be required to be familiar with, so that they would understand those concepts better. And educators trying to work with those students would be better prepared to present those ideas. We also have visualizations, some suggestions for some kinesthetic learning that gives people a better understanding of the abstractions that are associated with data types. So we're hopeful that through examining this chapter, it will inspire people to not only think about data structures in new ways, but also look for other literature and make connections with those various definitions that they will find, and understand these commonalities that are related to the topic. So once again, I thank you very much for giving us the opportunity, and we hope that people find this particular chapter and the entire book helpful.
Thank you so much, Rich and Baker. I know you're in the middle of your APSI training, teacher training, and you have made time to come here, and Baker wasn't able to make it. Thank you for presenting. Thank you for your chapter.
Thank you. Back to work for me.
All right, bye. Dave and Jen, you want to take it away? I'll stop share, sorry.
Yeah, you want to bring up the chapter 5, and then I'll share it right after you do that. I'm Dave Wolber from USF, and my co-author is Jen. Jen, you want to introduce yourself?
Sure. I'm Jen Rosato from the College of St. Scholastica. Nice to see you all.
Yeah, great to see everyone. We got a little video, so I'm going to share my screen, and hopefully this will work out okay. Building apps with user interfaces like an Asteroid game is not really something beginners can do with a traditional language like Java. But in event-based languages, it's doable because event handlers, like when a button is clicked, are primitive to the language. With Thunkable, for instance, you just drag out a when event block to specify an interactive behavior. Here, I'm coding when the go button is clicked, get the asteroid moving. The app can be tested immediately on your phone, so that, the screen on the right is showing my phone projected to the screen, and so that's how I could do the test. You can also code more sophisticated event handlers. In this second example, I'm coding when the asteroid hits an edge, move it to the top. And the response in this case is modify the Y property of the sprite to 10, and so then that asteroid is going to reappear at the top of the screen once it hits the bottom. Anyway, there's many reasons languages like Thunkable are great for beginners, but I think these when blocks, the event handlers, as primitive constructs in the language, are key to the whole thing, and they really help give beginners superpowers and the ability to learn by creating.
So let's think about teaching event-driven programming languages and about events. A nice way to start off is to demonstrate the app for the student. So Dave was showing how to build the app. You might start just by showing them how the app works and asking them to identify the different things that are on the screen that make up the user interface and the various things that they see happening on the screen. One tool that I've used before is a planning document similar to this. It's maybe a little more structured than you might want to do for all of your apps and event-driven programs, but it helps students organize their thinking. So you could have a space where they either draw the user interface or you provide it to them. There's tables on each side, one for them to identify the various components and the properties that they might set each component to. And then another part of the table there identifies the events that happen in the program and gives some space for students to write an algorithm so that they get to start thinking about how to plan their program.
Okay, so chapter 6, F is for feedback and formative assessment. Vicky Sedgwick and Kelly Powers are my co-authors for this chapter, and they bring deep classroom expertise in teaching CS and teaching teachers in primary and middle school grades. So this chapter is all about assessment for learning, and it shares the what, why, and how of formative feedback in the classroom. It draws on the idea of multifaceted systems of assessment that target the many facets of introductory programming, and it shares different types of formative assessment, and it shares many different examples of formative assessment. And the two that we're going to talk about today are quizzes, which are ideal for quick feedback. They are usually fixed response or multiple choice type, and they can be quickly graded or auto graded and given at the beginning or the end of a class period to get quick feedback on something you've just covered. And contrary to popular belief, they don't only test factual knowledge, but they can surface learner difficulties and problems with understanding. So they can be framed in various ways. It could be a code snippet that has a bug, and the student has to identify the bug and maybe fix it. It could involve a Parsons puzzle, where students have to rearrange blocks of code to represent the correct solution. They could be code snippets that are entered by students that are unit tested and auto graded, or it could even be a simple 2-command question like this that actually reveals students' understanding about things like variable assignment. And next, Vicky and Kelly are going to talk you through programming projects.
Beyond quizzes, there's feedback that students and teachers get from assessments of programming that's done by students. Like quizzes, these can be a variety of different types, from debugging all the way to an open-ended original programming project. Original programming projects are rich for showcases and for getting feedback from peers and for self-reflection. Programming projects should also be accompanied by a rubric. We often think of rubrics as summative, but they are also good for formative assessments, as well as peer and self-assessment. Code reviews are also helpful in identifying what a student understands and doesn't understand about the code they've written. There are many ways of doing code reviews, from student presentation to written documentation, as shown here.
Peer feedback and self-reflection should be built into a programming project as milestones, allowing students to reflect, receive, respond to feedback, and iterate on their work before the project ends. These two artifacts highlight the 4 aspects of formative assessment. Students use a showcase presentation protocol to share their project with their classmates and call on the audience to ask questions during the live session. Engagement soars, and students reflect as a class at the end of the showcase to see how they can improve the project for the next time.
For this and more, check out our chapter.
So this chapter is actually all about how to write programs by not writing programs. So the focus is actually about guided exploration through unplugged activities. So in particular, it's about how important it is to get away from the computer if you're going to learn to program well, so that the focus is on concepts and understanding the concepts, not just exploring and not really understanding the detail of what you're doing. So the chapter sort of looks at several different kinds of unplugged activities, including role play activities where people act out computation. So there's no reason why programs have to be compiled onto computers. They can be compiled onto people, and the people can do the actions, and that gives a very strong way of starting to understand exactly what they're doing and how they're doing it, rather than being in a black box that you can't really tell what's really happening. We talk about memorable stories. We talk about using games and puzzles, and also about the importance of written and verbal explanations as part of making sure this focus on concepts leads to a deep understanding of the concepts to give a strong foundation for when you are actually programming through exploration of writing code. So it's all about how unplugged activities can provide some structure that is really complementary to actually writing code that helps form that guided part. So it's based on a bunch of activities. So ones I've contributed are basically from my CS Fund Teaching London Computing project, and Shuchi has also provided ones from her project. So we look at a series of actual example unplugged activities. So box variables is a way of doing role playing, for example. Locked in 20 questions is actually something that goes with the storytelling idea. So just to sort of give an idea of that, that's partly about the idea of actually putting sort of story narratives around understanding programming. So my favorite one of this, which is actually talked about in the book, is actually based on a book called The Diving Bell and the Butterfly, which is the autobiography of Jean-Dominique Bauby, who actually had locked-in syndrome, which is total paralysis, and about how you could possibly write a book with total paralysis. So in one sense, it's not about computing at all, but as you go through the story, you unlock lots of issues that actually are computational thinking, computing issues, and those are actually illustrated with specific activities like playing a game of 20 questions and doing some role play activity. So that sort of sums up a combination of things. Other activities are playing Simon Says as a game activity, and another story-based one about story variables, where you're aiming to sort of understand variables and their role in programs by telling stories about some variables that actually change as the story, so things that change value as the story progresses. So it's all about how you can use these kinds of activities to get a deeper understanding of concepts. And in the chapter we also talk about the links of this to semantic waves, which is a theory by Carl Maton, which is all about what makes a sort of good learning experience. And what this says is basically good learning experiences should follow a wave-like structure, or possibly a series of waves, where you start with abstract concepts and then you unpack those concepts using things like unplugged activities and examples, diagrams, metaphors, and that takes you down to concrete things, the things the learner already understands or can easily understand. But then the really important thing is you go back up and repack those concepts, do activities that actually repack back up to the abstract concepts and the technical language. So it's all about how you gain mastery of the language. And so if you apply this kind of approach, this theory, to the way you use unplugged activities, it gives you a way of giving you more chance that the unplugged activities aren't just playing the games, and you are actually linking them to the technical language and the abstract concepts that you're really trying to teach. And so the chapter actually ends with a whole series of do's and don'ts that are based on this theory of semantic waves that suggests these approaches and ways to structure activities and to make sure your activities do give a good guided exploration experience. And that's basically it.
This is a chapter I wrote with Deborah Fields, and it kind of summarizes our experiences. How do we actually teach algorithm, data structure, and all these things which are mentioned in the book within a classroom project? So, and what we put into the chapter are principles which we had learned by putting the electronic textiles into a curriculum for the Exploring Computer Science yearly plan. And we distilled this in 6 principles. One of them is promoting creativity within constraints, and that connects nicely back to Miles Berry's presentation on creative coding. So how do you actually kind of get kids to have some degrees of freedom on what they program, but also cover important concepts. So we have some ideas on how you can kind of manage to do those 2 things. A second principle which we developed was growing complexity in a series of projects, and you see some examples to the left on the screen. So starting with the most complex activity actually doesn't work very well, because the students, in particular in physical computing like electronic textiles, but also other areas, actually need some experience in understanding circuits, in learning how to craft and sew. So we learned the hard way that the most difficult project needs to come at the end, and that we needed to kind of scaffold the activities in a series of projects which get increasingly more complex, so that students at the end can successfully deal with more complex projects. And the third principle is equally important. It means starting with aesthetic first. Often in computer science, we're so driven to get students to understand complex concepts, but we actually suggest that if you want students to work on projects of their ideas, to start with the aesthetics first and then worry about technical aspects or concepts later on. Because if you do it the other way, kids kind of get stuck and don't really think about what they're interested in. A fourth point is about celebrating mistakes. Yes, programming mistakes, debugging happens all the time. And rather than to see them as a stumbling block, we suggest to have a hall of errors, of actually having students share the problems they have, as also the solutions they have come up with. In most beginners projects, students have maybe, a few experiences of bugs, but by opening it up to the whole class, they get a wider range of experiences of what other problems and solutions students have come up with. Keeping track of progress is equally important. And then finally, reflecting as computational communication, we also build in portfolios where students also keep track of their projects and then reflect on the things they designed and built. Finally, if you want to find an example, so the Stitching the Loop curriculum for electronic textiles is available online, where you can see how we actually designed the whole curriculum, the different rubrics, assessments, and activities. There are videos. And also we have create expansion unit. We work with different Arduino platforms. So you have multiple examples of how you can actually make that work. Thank you.
Thank you, Yasmin. And as you can see, something that I didn't say in the introduction, but this idea that there's so many pedagogies to teaching programming, and I think we have captured all of them in this book. And certainly Yasmin and Miles' chapter speak to the idea of constructionist learning, as will Sue's chapter. Anyway, so moving on, chapter 9 is on integration of programming into other subjects, which is a topic of growing interest in the CSED community. And the starting point of this chapter as well is Seymour Papert's philosophy that teaching children to code provides them with the means to experience and experiment with powerful ideas in other subjects. And he, of course, worked extensively with children developing mathematical thinking through programming and Logo. And the chapter even touches briefly on the idea of turtle geometry, the origins of Scratch, and the other languages for children that come out of MIT. The chapter shares benefits and challenges of integration. We talk about the challenges with some suggestions for what potential solutions might be to addressing them. And these challenges are real. I heard them even at CSTA at Bill Marsland's and Jake's presentation on integration. So the bulk of the chapter is really about examples, concrete examples for different grade levels, and with contributions from many in the field who we approached to share their example projects. So it talks about the very successful bootstrap curriculum, for example, for algebra and physics and data science, integrating coding into those subjects. Talks about the work from Northwestern University, Vanderbilt University, media computation from Georgia Tech, Project GUTS, the STEM coding project. And so a few examples. There are many math examples in addition to projects on probability and proportionality and geometry. We describe in detail this really fun example from Don Dupriest on physical computing that uses the BBC microbit with Python code to make a trigonometry lesson come alive by having students calculate the height of a building. For language arts, we have several cool examples that bring the idea of sequencing and conditionals and even data structures. The social studies examples are very cool. They talk about interactive timelines, and this really nice project from Utah State University called Colby Toffel-Greel and Kristen Searle's example with the E-Stitch curriculum, where they have students design and construct and code interesting artifacts and timelines with paper circuits and e-textiles that showcase, widely varied stories of American migration and immigration and enslavement. Such as this one based on A Place Where Sunflowers Grow by Amy Ty, and this one on the Underground Railroad. And there's also an example from computational journalism that uses Python scripts to scrape web data and interrogate ideas of social justice. Examples from science, of course, lots of work on how agent-based modeling and programming in NetLogo and StarLogo has transformed science classrooms. And finally, music. Props to Jared O'Leary and Jens Monig, who shared excellent examples in Scratch and Sonic Pi and Snap that recreate known melodies and also demonstrate how to create new notes and their own notes and alloteric music based on the random number generator. And had this tweet that came out today, on how Taylor Swift's song "Shake It Off" can be coded in JavaScript. Had this been there, it probably might have made it to the book as well. So that's it.
Right. My name is David Weintraub. I'm faculty at University of Maryland, and I had the great pleasure of getting to co-author a chapter with our fearless leader, Shuchi, and that chapter is titled "JavaScript, Python, Scratch, or Something Else: Navigating the Bustling World of Introductory Programming Languages." Do people see the title slide here? This looks good. All right, some thumbs up. Okay, so the problem that we were trying to tackle with this chapter is the recognition that when teachers set out to teach computer science, at some point they are going to be confronted with this consequential decision of deciding what programming language to use, what environment, what tools. And there was a time where this was maybe not a totally straightforward decision, but there was maybe one or two choices to choose from, and they kind of look the same, and it's just a matter of like where the semicolon and curly braces go. That decision now is made much more complicated because now it's not just picking a language, it's also picking a modality between graphical and text-based. It's trying to decide if you want to be physical, include physical robotics and tangible computing, or be all virtual. So the goal of this chapter is to try and not necessarily tell teachers what the right answer is, because that would be very fun, but instead to kind of lay out a set of resources and provide teachers with ways to help them make informed decisions. So the way that we went about doing that was first to kind of lay out a set of dimensions that are worth considering when trying to decide what environments to use. And so for each of these dimensions, we talk a little bit about where the ideas came from and why we think they're important. So the first dimension to consider is the idea of low floors, which again harkens back to Papert and early logo work, which is thinking about ways to make the programming, or how the programming environment is accessible to novices. What are the various on-ramps? How can it be intuitive and easy for those who are just getting started on their computing careers? So that's a first dimension. A second complementary dimension of low floors is high ceilings and expressive power. And so this is in considering what environments to use, thinking about kind of how far you might be able to go with it. Is it important for people to be able to do quote unquote kind of authentic professional style programming, or is it sufficient for learners to kind of be more focused on engagement and expressivity in terms of the things that they're interested and care about? So second dimension is high ceilings and expressive power. The third is the idea of wide walls and a diversity of artifacts. The tool that you choose, are you able to make a wide variety of different types of projects, or all the projects that you're going to make with it more or less going to look the same? And so thinking about, is this something that you think will be important for your learners, that they can kind of really insert themselves into the tools being made and create artifacts that really resonate with who they are and what they care about? Or is it more important to have some consistency across the classroom? A fourth dimension to consider are the social aspects of the environment. Are there characteristics of the environment or the larger ecosystem that it's situated within that will allow learners to share ideas with each other, to present the work that they're doing, to collaborate, to remix, to talk about, to present the project that they're making? And so thinking through, is that something that's important? And if so, what would that look like for the various tools that you're considering? A fifth dimension is not necessarily a characteristic of the environment itself, but instead thinking about curricula and supporting materials, again, thinking about the larger ecosystem that it's situated within. Some environments might be really cool and exciting, but have very little in the way of curricula that go along with it or supporting materials. You might be directed to a GitHub repository that you have to like compile and host on your own, versus other really mature environments that have textbooks and examples that go along with it, and assessments and et cetera. So another dimension to consider in terms of deciding what tools to use is kind of the supporting materials that go along with it. And then the last dimension that we discuss is this idea of preparation for future learning. And that's thinking about, in deciding what tool you're going to use for your learners, what trajectory might it put those learners on, and in what ways might it connect with future types of learning future learning opportunities that they'll have, be it in computer science or beyond. And so thinking about what that might be for the environments that you're using. So in our chapter, we go through all these dimensions and kind of talk about why we think they're important and what they look like. And then in the second half of the chapter, we walk through not necessarily specific environments, but kind of families of environments and what those different dimensions look like within those families. So we spend some time talking about block-based languages and what those various dimensions look like, and kind of where block-based languages excel versus where there might be some drawbacks. Then naturally spend some time talking about text-based languages, again, through the lens of the various dimensions that we articulate at the start of the chapter. Pre-literate and symbolic languages, this is the thing about the youngest learners. What are characteristics of environments for learners that don't have this built-in dependency on reading and literacy skills? And then finally, physical computing. And we think about physical computing very broadly, but what are the various affordances as it relates to those dimensions that we outlined? So ultimately, the goal of this chapter is to take teachers from this place where they're feeling kind of overwhelmed and unsure to a place where they're more excited about all the different tools that exist, and kind of thinking about how they can bring in different ideas to their classroom to get their kids excited about the world of computing. So that's our chapter. Shuchi, since you're here, anything to add? Put you on the spot?
No, that's it. You did a great job, David. Thank you so much.
Great. Thanks, and very nice seeing everyone.
And I do want to add actually that at the end we do at the end of several chapters we add a list of resources to turn to for more further reading, and this is also one of those chapters that has a ton of references at the end that folks can refer to.
I'm Rebecca Vivian, and I co-authored this chapter with my colleagues Shuchi Grover and Katrina Faulkner. So in this chapter, we're really looking at our goal as educators is to help students grow into confident learners and programmers with increased interest and agency in the learning process, ensuring that students have the necessary knowledge and skills to design, build, and test their programming solutions, including positive attitudes and beliefs that support the development of resilient learners. So this chapter outlines key knowledge and skills, as well as the positive attitudes, beliefs, and mindsets related to programming. It brings teachers up to speed with the fundamentals that underpin programming education, and we support teachers with analogies and a toolkit of strategies that they can use to grow student learning. Additionally, pedagogies must scaffold thinking and programming skills and development of positive mindsets towards computing and programming. This chapter has been developed around the deeper learning framework, so looking at the cognitive domain, which includes students' thinking, reasoning, and disciplinary skills, the interpersonal domain, which includes collaboration and communication, the intrapersonal domain, which involves students' beliefs and mindsets, and so on towards programming. In much the same way as in English has rules and conventions for writing, effective coding mandates those unique rules and conventions as well. So we highlight the importance of these and how teachers can guide the development of good practices, pointing to further learning in other chapters. Computational thinking, systems thinking, and design thinking underpin the learning of programming or the creation of digital solutions. And we can explicitly integrate the teaching of these skills into computing education to improve learning and build students' capacity in these various ways of thinking. And we present each thinking skill with a breakdown of the stages, the key elements, and practical classroom examples at each stage. So as seen on the table here for computational thinking. The goal of programming in classrooms should be to empower students to have control over their learning by building resilience and autonomy in their ability to tackle problems through problem solving, and by building self-efficacy, motivation, good study habits and mindsets. The teacher can design learning activities and environments to really cultivate these practices and mindsets. In making learning environments inclusive, we're not only creating a space where underrepresented groups feel like they belong and can develop interest and a sense of identity in programming, but one where all students may flourish. And we also point to chapter 12, where teachers can learn more about culturally relevant approaches to programming. Programming is not only about communicating to the computer what we want it to do, a large part also involves communicating our code and our programs to humans, and also working alongside others to create solutions. We propose practical ideas for how students can develop and engage these behaviours, for example, code commenting or through feedback loops. And many of the topics overall in this chapter provide a foundation to the fundamental knowledge, skills and attitudes and beliefs that students are to develop through programming. We cite some initial classroom ideas that teachers can implement, but also point to other excellent chapters for deeper learning. And that's all for my chapter. Thank you.
Can everyone see the slides? Hopefully so. Okay. Great. Well, Jaquita, Jessica, Joanna, Frida, and I are thrilled to share this work with you, and we want to say thank you to Shuchi for leading us in this effort, and congrats to all the authors involved. This chapter was generated from our collective research focused on equity pedagogies, which are essentially assets-based approaches to working with minoritized students, or what some folks might commonly say as students of color. We're thinking about justice-oriented approaches. And in our chapter, we highlight how educators can move beyond an access and achievement frame for thinking about programming and kind of the pedagogies that they use, to really focusing on empowering students and taking up justice-oriented approaches and programming as we work with learners. We see educators using this chapter in a few ways. One is to understand what culturally relevant pedagogy is and what learner-centered pedagogies look like, why it's important to use it in programming and computer science classrooms, what it can do for students, especially our students from minoritized communities or students of color. We hope you enjoy it and we welcome your feedback. And now I'm going to give it over to Frida as we move into the key takeaways from our chapter.
Thank you, Tia, so much for that introduction. We decided to present collaboratively because that's how we made the chapter. And while I get started, I just want to first recognize that we're living in very different circumstances than when we wrote the chapter of this book. We're living through an extraordinary and urgent time for our schools and communities in the US. So while all schools are impacted by COVID-19 this year, schools and communities of color are bearing the brunt of the global pandemic. At the same time, they're experiencing racial trauma through the recent high-profile murders of Black men, women, and children by police. So both COVID-19 and the George Floyd uprisings have brought to the public attention many historic and ongoing health and economic inequities faced by schools and communities of color. So while we're considering what equitable teaching practices look like, we want to be clear about the moment that we're in and to recognize that massive investments need to be made in communities of color in order to address these inequities. Underrepresented students of color deserve and need much more from all of us to make schools and classrooms the safe, warm, and welcoming environment that we all want them to be. So we wanted to just share a little bit about what culturally relevant pedagogies is, and in the simplest form, it's the idea of connecting computer science concepts and principles with students' lived experiences and cultural backgrounds. And I'll give it back to Tia to talk about the last bullet on this slide.
Yeah, and so we see teachers using culturally relevant pedagogy, or CRP, for computer science and programming in order to connect with students' cultures and life experiences, we really hope that that tenet around building on students' cultural practices, right, and not in ways that appropriate and help make connections between those ideas and what we're teaching in the classroom, so the content. We also see CRP empowering students to become change agents, and so that's thinking about the ways in which they can use their programming knowledge to change our world. So for example, we've shared with students, other students their same age who have developed apps to document police brutality, students who have developed all manner of technologies that support their communities and solve problems that are relevant to them. And that's what we mean by empowering students. And then most importantly, building relationships with students, families, and communities.
We wanted to give you all some ways to plug in. So the K4 Center has started an initiative we're calling the Equitable Computer Science Curriculum Initiative. You can find us online by Googling that. I guess you can't click this link because it's screen shared. But if you want to sign up for the forthcoming e-newsletter, and then there's a series of webinars. This project is designed to build a national framework on what culturally relevant pedagogies in CS could mean. We also have for Bay Area folks and folks who are interested in supporting Bay Area students, the Rising AP STEM Scholars Initiative, where you can mentor underrepresented students of color. And then, of course, Tia was thoughtful to include our Twitter handles. There are 4 out of the 5 of us who are active on Twitter, so please do check out, follow, and support our work and be part of our community through that too.
Yeah, and we'll
Thank you
share
all
this
so much.
information from this slide on our Twitter feed, so look out for that. Thank you.
Brilliant. Thanks.
Thank you so much, Tia, Frida, and Jaquita, and Joanna, and Jessica, and of course, all the folks whose work you drew on for this chapter, including Yolanda and Kimberly Scott and Alison Scott and others. So the next chapter, we're on to M, modularity from with methods and functions. And Mike, you want me to share the screen?
Hey everybody, I'm Mike, and Jens and John Alf and I are really excited to take part in this project, doing the chapter on functions. Such a cool project to be invited to take part of. So many accomplished people, and more importantly, so many good people are working on this, and that's just so cool. Let's jump it off looking at this chapter, and I wasn't going to say it, but I guess I have to. That we're going to put the fun into functions. Okay, I'm sorry. All right, so basically functions allow you to modularize your program, break it up into chunks. And when I started, I used a language called BASIC, and it looked a little bit like this, and I used a computer affectionately known as the Trash 80, and I was a kid, and we used to type in these programs. We'd literally type them in, from a magazine like Creative Computing, or I forget the names of the other ones, and the code, you'd see it like you'd start at the top, and then maybe you get down to here, and you jump up to here, and then over to here, and it made really, really hard to see what was going on and to understand and to reason about a large program or to write something successfully. But then functions came in. And with functions, or then I learned about functions, with functions you can break up your code. You can have some code and you can have another chunk of code. Maybe this does certain things. Maybe this does the user interface. Maybe this does the mathy stuff. And you can basically say, oh, I need to do some code for more code. So I'll go over there, do my thing and come back. And then I'll go over here, do my thing and come back. And this let you make larger programs by multiple people, more maintainable, easier to reason with. And you could even do things like call yourself, and there's a recursion chapter that talks about that. So functions let you do all of this. The problem is when you're teaching it, you're either going to teach constructs first, like ifs and whiles, or functions first. But if you write constructs first, they're resistant to learning how to write functions. And if you do functions first, there's nothing that you can do with them. You don't know any statements. So what we've done in the chapter is we've talked about incremental problems with reusable pieces, things you can do without knowing all these language constructs to encourage students to learn how to use functions, and also in addition to using them so they don't get these big monolithic programs, we also talk about some of the challenges, some of the difficulties the students have. So I wanted to keep this short, and I think we managed that. So check out the chapter, check out the rest of the books, and thank you everybody for including us on this project.
Thank you, Mike and Jens and John Alf. Juha, you're going to share your screen? And we have chapter 14, Naive Conceptions, and here is Juha.
Hello, I'm Juha from Finland, and one way to look at my chapter is that it says that many things are great. First and foremost, finding out your students' conceptions about programming concepts is great, because that helps you teach your students better. Also, the number of so-called misconceptions that students have about basic concepts is great. This chapter covers quite a few of those. The impact of students' prior knowledge on their learning of programming is great. Students bring in math, they bring in natural language, they bring in their experience of various everyday phenomena, and all of that impacts on how they perceive programming concepts. The number of example programs that students should see and work on is great. There's a ton of things to learn. There's a lot of these little subtle nuances that students need to come to appreciate, and there's many pitfalls to avoid, and that takes a bunch of examples. This chapter illustrates some of that. Deliberately teaching students a way to reason about program behavior is great. Students will try to reason about program behavior in any case, and in order for them to have a good chance of success and to avoid unproductive failure, they need help with that. Expressions, values, and evaluation are great and sometimes undervalued concepts. They're great because they help us look inside what goes on in a line of code. They help us avoid a bunch of pitfalls, and they help us understand how and why constructs can be combined in a program. Using a REPL, an interactive interpreter, is great because it helps students study all those little examples that they need, and because it helps them experiment very easily. Scaffolded tracing, explaining code completion, fixing, debugging activities are all great when you manage to motivate them well enough so that students actually engage in these activities. Drawing attention to the literal versus non-literal language that we use about programming and programs is great, but I don't have the time to go into the details here. Using analogies carefully is great. Well, you can explore with your students how an analogy fits and how the analogy does not fit. I don't seem to have spent my 3 minutes yet, so that's great. And finally, the fact that this book has been published is great, and I hope you enjoy and find it useful. Thank you.
So, yeah, I agree with you, Shuchi. Juha's talk was great. And I think the chapter must be great. I really want to read it. I hope the book arrives soon. So I'm going to talk about something else here, but adopting Juha's language, let me say expressions are great. They are of great value because they can be evaluated and they give you values. And that's kind of the core idea of expressions. So in this chapter, we talk about different things with respect to expressions. For example, we talk about expressions in different programming languages because they appear in every language. I mean, there's no language I know of that doesn't have expressions in there. And some programming languages have nothing else. It's just an expression, right? If you go into extreme functional programming, everything is an expression. So they're kind of a great tool in the language. One of the things we focus on in the chapter is how to represent expressions. You could call it, following Juha, a kind of notional machines, maybe to some degree, visual representations. Some of them are actually used in the kind of IDEs you use, like if you play with Scratch or Snap, then the blocks are nested according to the structure of the expression. You plug sub-expressions into those holes in the blocks. If you follow the bootstrap curriculum, for example, then they draw those circles of evaluations where the parentheses of scheme become circles and are nested accordingly, and then they explain how they get evaluated. Another way to represent an expression is as a tree, computer science upside down tree, and then you can say evaluation actually goes bottom up in that tree, and you can make it explicit, you can explain it to students how those values come out of those expressions. Another part of the chapter is activities. I think there are some fun activities like playing with dice or talking about pool. Also about expressions being used not just to do arithmetic, but you do expressions also for Boolean expressions, like for conditional statements. And speaking about that, that's a little bit of a misconception that expressions would only be for arithmetic. So we talk about a sequence of misconceptions that are specific to expressions. For example, that a single thing like the number 15, that sometimes students think this is not an expression, that's just a number. But even a number is an expression, it's kind of an atomic one. And so we point to a website that has a list of those expressions also with more information. But the chapter lists the key ones about expressions. That's it.
Thank you. Thank you, Matthias. It was great collaborating with you on this work, on this chapter.
It was great, Shuchi.
The next up is Shannon and Jill presenting on pair programming.
I'm Shannon Campion from ETR, and I think a lot of you know Jill, and some of you know me. We've been working together for about 20 years, mostly with upper elementary to high school students, and teaching programming in different ways and studying it. So we've done a lot using pair programming in different settings, informal and not, and we ended up getting a whole research project just about to study pair programming really in depth. So what we really want to do with this project was finally get some of this information out to teachers and have it really be something that's usable for them, because, you know, we all know that, I think we all know what pair programming is, right? So the book kind of goes over, the chapter goes over, you know, like what is it exactly and kind of the basics of that for an educator that would want to give it a go, and kind of ideas of like why to do it and where the value is in doing it. But as we all know, sometimes it looks like this, and it's so exciting, and kids are building off each other, and they're challenging, you know, their own, you know, learning, and they're growing, and they're having fun, and we're like, oh, they're doing it. And then, you know, then we have a lot of this where kids are disengaged, and they're not really collaborating, they're not really working together, they end up kind of solo programming or even like almost parallel programming next to each other. So this chapter kind of goes over being really intentional about, if you choose to do this, kind of why you want to do it, and then how you want to do it. We ended up making a toolkit that's free, and it's on the ETR website, that basically this chapter is a lot of what's in the toolkit, but the toolkit also has lessons and such. So you're really being intentional, kind of how you're pairing the kids, how you're teaching them to do it, because kids are coming from different backgrounds, of course, of collaboration experience, and then supporting them through that. And we do some, like we have always done some off-computer activities too, to work on kind of communication and role plays and such, to really see what it looks like when it's going in a more effective direction and what it looks like when it's not going in such an effective direction. So the chapter kind of outlines this, but doesn't go into all the details. That's in the toolkit. The chapter also is just a snippet from the book, right, of like for what collaborative behaviors look like for the navigator, for the driver, and for both of them. And then also what the non-collaborative behaviors look like for the driver and the navigator, the both of them. Again, a lot of you, if you've already done any of this kind of pair group work, you've seen a lot of this. So it's just a way for teachers to really here's some specific examples of things we've seen, and people that have, there's many other people that have done the work too that have seen. And then we go into a little more, because usually the big jam is always that there's still these kids that are struggling. And so we give some kind of more specifics of, like, if you're observing this, here's some questions you can ask to really get at it. And so I mean, like I said, I think it's varied how well it can work. I think it takes a lot of intentionality, and I think it takes a lot of commitment from the teacher or the educator to help it happen. But when it does happen, it can be really effective for the kids. So hopefully this is something I love the book, Shuchi. I love all the color coding. It's so easy to follow, and it's really digestible. And I just want to say, as a past teacher myself, that's super important. So
I just wanted a quick thanks to Shuchi, of course. I had the pleasure of co-authoring chapter 17 with her. I also thought I'd take this chance to a little shout out, a thank you to Todd Lash. Todd is out there somewhere. Todd, to me, exemplifies this community of practice. I met Todd a few years ago, and he's helped me step through the process of moving from computer science teacher to PhD student to PhD applicant to PhD student to PhD candidate. And he just kind of exemplifies this community. So I just thought I'd kind of give a quick thank you to him. Our chapter 17, myself and Shuchi Grover, we wrote questions and inquiry. So this chapter, we focus on two aspects of inquiry. We focus on how teachers can use questions to prompt discussions and promote deeper engagement, and how teachers can respond to student questions. So there's three main parts here. Part 0 looks at questions teachers ask themselves and of the lesson plan. So helping the computer science teacher be sort of a reflective practitioner. And I remember this myself, driving to work or driving home from work before or after teaching a lesson, and just those questions that are reeling around in my head, whether the activity went well or did not go well. Part 1 discusses questions to foster inquiry, prompt discussion, and deeper understanding. And then part 2 looks at student questions and how we might respond to the different student questions that arise in the computer science classrooms. Questions teachers ask themselves and of the lesson plans. We look at questions like, how can I make this lesson more inclusive? How can I ensure that opportunities exist for creativity and innovation? How can I ensure that examples accommodate student backgrounds? Considering prior knowledge, how does this build on prior work? In part 1, we discuss questions to foster inquiry, prompt discussion, and deeper understanding. And there's 5 examples in that part of the chapter. Questions to help students plan a solution, probing questions about a code snippet, evaluating alternative solutions, artifact-based questions, and questions based on buggy programs. And then in part 2, we discuss student questions, whether they're questions around algorithm design, data structures, even just syntax. And we ask whether the instructor or the teacher should be responding to all those questions in the same way. If there's times where they should be providing more information, times they should be providing less information. And we talk about considering the type of question being asked, consider the learning goals of the lesson, and considering the students themselves. That's a quick roundup of chapter 17. It has arrived here in Canada. I've been walking around the house reading it out loud to my kids. They like that at the start. I think they're getting a little tired of it now. But it's been a real pleasure. And yeah, thanks again, Shuchi. Thanks for everything.
Next up is Shannon and Jill presenting on pair programming.
He's Dan. I'm Josh. We have 3 minutes to talk repetition and recursion, so let's rock. When we need to do something many times, we can choose between iteration, such as loops, and recursion. So which should we choose and why? And it depends on how you think about a problem. Let's consider the problem of writing a factorial function as a quick case study. Whoops, there we go. So if we think of the definition of factorial, we might note that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is also 6 times 5 factorial. And if you look at it that way, then the general case emerges where n factorial is the same thing as n times n minus 1 factorial. It should have been in this slide, sorry about that. And the smallest examples we can come up with are 0 factorial and 1 factorial, both of which are 1. And when we look at it that way, the code almost writes itself. If we've got a situation where our n is 0 or 1, we just get a 1 back. And if we have something that's bigger than that, we take our number and multiply it by, n minus 1 factorial. And voila, we have recursion without really having to talk about the word recursion at all. Iteration is also good. Another way to go and set this up is to go and have a holder, such as the variable product here, which we initialize to the multiplicative identity. And then we grab all the numbers from 1 up to n, and we multiply that product by each of those numbers. And when we've done that, we're done. And so in this particular case, we have a for loop, which is a rather conventional thing, and that works great also. Just depends on how you approach the problem. We also have this bonus approach, this idea of a higher order function, which fits in the functional programming paradigm, doesn't involve assignment operators, much like the recursion example, and allows us to think abstractly all the way. So one way we could think about it is if we could just take all the numbers between 1 and n and reduce them by means of multiplication, we'd be done. And voila, we get this in one line. So there is, once again, another example of doing something over and over again, but we've got it abstracted away using this lovely function reduce. Okay. All these techniques are really useful, for a programmer to have in their cognitive toolkit, but they're not always created equal in the problem-solving process. For a brief discussion of that, here's the lovely Dan Garcia.
Thank you, Josh. So we realized, let's find a problem that's really beautiful, just elegant, just dripping with elegance to be written recursively, that's really hard iteratively. And so this is an example we came up with, which is how Josh, by the way, he should tell the story, on day 1 of his computer science class, he teaches the recursive tree. You've got to see that's a work of beauty to watch Josh do it. So this is the code on the right, is the code that they eventually write, and I added a delay so it slows it down. And it basically does what we call in computer science a depth first search. It goes down to the end, then backs up. And the thing about recursion is, when you make a recursive call, you've got to know how to come back. And this is even the functional chapter. Once you make a function call, you go somewhere else, right? Remember, I love Mike's talked about, in BASIC. I learned in BASIC also. When you do a go-to, you got to be able to go back. There's a go sub. So how do you return back to where? Somebody's got to keep track of where you were. And if you have A calls B, calls C, calls D, there's a lot of stuff to remember how to come back. And all that is taken care of by the system. Well, if you use iteration to do this, and this is in this Turtle Graphics example, you have to manually manage the how to go back. And so we do this in this way by kind of having a list of things I got to do. And every time you get to the end of one of the forks, you got to queue up. You got to remember 2 more things. Like, well, I better make a tree on the left and a tree on the right. And so all this ugly code on the left is the code that has to do the thing that recursion does for free. So there are a lot of cases like this where the amount of code, and I can't imagine anybody wanting to have the code on the left versus the code on the right for readability, for manageability, for handing it off to your other teammate. There might be some issues that we're going to talk about in a moment about the stack might be overwhelmed, and that's the invention of the one on the left. And also, you can kind of pause it and restart it, because remember, the computer is keeping track of the frames, the stack, the kind of where you were. And if you crash, you lose it. But if you were kind of doing it on the left and remembering it, writing to a file, you can restart this. Next slide. So, TLDR, as you're a teacher thinking about how to teach this and balance this, the most important thing you can tell all your students, and you should know yourself and write this on the wall, is any problem can be solved using either repetition, i.e. iteration, or recursion. That's the fundamental thing that you got to make sure that your students walk away knowing. You probably are going to, for most of the problems, choose iteration. You've got issues of the stack frames, which may overwhelm if you just kind of have a loop that's really long and the recursive thing is going to go really long. That's an issue. If you ever try to write Fibonacci recursively, you can't even do more than 30. It's a little ridiculous. I can write down, my daughter, when she was in 4th grade, wrote down all the Fibonacci's of 30 just by doing one after the other, using a little pattern. Well, the next number is the sum of the previous 2 numbers. She got to 30, and I showed her that her computer couldn't even do up to 30. So there's also an issue of speed. But that's not maybe the most important thing to consider. The one you want to think about recursion first is if you've got a recursive data structure like a tree or some kind of recursive structure, like even a linked list can be done recursively, even cleaner. Often they're more elegant, as I showed you the code before. Some programs are screaming to be done recursion. And even stepping back, as Josh pointed out, even better, let somebody else worry about it. I love the idea. It's not my job, man, which is let somebody else, Freddie Prinze, let somebody else do the work. And that's the idea of higher order functions. However, and by the way, however they wrote it is however they wrote it, but you don't have to worry about it. You just call reduce, which is really beautiful. at the end of the day, you got to decide what the purpose of your code is. Is it for tutorials? Is it for speed? Is he running a graphics thing? Is it for the GPU? And think about what the right kind of tool is for that. And as you're thinking about this, Josh and I came up with an analogy, which is you can put, if salt is iteration and sugar is recursion, you can put both of those things on any food you've got, but kind of food will taste better if you pick the right one. And we were thinking about what's the analogy for higher order functions and what works both, well on food that needs salt or food that needs sugar. And if you deep fry, who is my friends from the South? If you deep fry food, I've had the most delicious deep fried ice cream and deep fried salty stuff, and they're amazing. So higher order functions are the deep frying of the analogy, and decide what you want to do. Thank you very much. My name is Dan Garcia, and I approve this message.
Thank you so much. I have to say that the idea of the quotes came from Dan Garcia and George Bailey's chapter. They were the first ones to send their draft chapter with the pithy quote, there is joy in repetition by Prince. And I was like, that's nice. We can add some quotes to every chapter. And I think it turned out quite well.
And we also wanted to thank you, Shuchi, for being part of the team. This is a delightful book where we think this is a fundamental breakthrough book, and hashtag CS for all, everybody. Love it.
Absolutely. Absolutely.
It's worth noting that something that's so comprehensive and deals with pedagogy is such a refreshing thing compared to, which tool should I choose to teach my class.
Woo!
Thank you so much for doing this.
Thank you so much.
Thank you. Thank you, Josh. Thank you, everyone. So S is for selection, aka conditionals. Like many other concepts chapters, this one talks about the structure of the conditional first and what the if-then constructs look like, the condition in the conditional, and how closely it is tied to an understanding of expressions. And so there's broad tips for teaching conditionals like visualizing pathways, and several examples are recommended. When you're teaching conditionals, have students think about just if-thens, if-then-elses, things that are before, after, and have them visualize what each of those pathways will be, the flow of control. Everyday examples are great because if-then logic is so natural, it comes so naturally to us on a day-to-day basis. There are interesting coding projects that the chapter shares, like rock, paper, scissors, and it's others that, to use Dan Garcia's phrase, scream, you need to use conditionals for those chapters. So here's an everyday example, a cheesy one. I'm sure some of you are going har, but if you're a school teacher teaching or working in CSN, this book will be useful to you. A lot of us think, and actually research has also borne this out, that conditionals come fairly easily to children. As a concept, they don't find it very difficult. But even so, some children do struggle with some of the ideas. What, for example, is the difference between a series of if-thens versus nested if-then-elses? And so the idea of efficiency of a program having to execute each of those if-thens versus if they are put in as if-then-elses. And also other ideas like, understanding of compound expressions, how to construct that expression, redundancy. Sometimes a student will check for x less than y and y less than x, incorrect order of precedence in compound conditions, and such. So that's it for me for this chapter. So I'll stop sharing.
We are ready, and I'm just going to start talking while we're waiting for the share to work. My name is Katie Rich. I am a DOC candidate at Michigan State University in educational technology, but I came to that work with a background in research-based curriculum development, primarily in mathematics, but also in computer science at the elementary level.
And I'm Carla Strickland. I consider myself a STEMinist. I work in diverse primary and secondary classrooms from my native Trinidad and Tobago to the United States. Teaching students, coaching, and delivering professional development to teachers and writing curriculum. In the last several years, my colleagues and I have been researching integrated computer science education. Katie is one of my favorite people, and we co-authored Chapter 20, Testing and Debugging.
So this introduction to our chapter, as you might expect, sort of focuses on why it's important to test and debug your programs. But then we move into two other major points that we hope that teachers take away from reading our chapter. So first, we include a collection of strategies for debugging. We worked really hard at finding the right level of specificity for these. On one hand, we wanted to make sure we were sort of unpacking the process of debugging a bit, demystifying it, trying to make it less of a black box. We know debugging can be frustrating, especially for beginners and for teachers who are just starting, but we promise there are ways to think about debugging that don't just involve staring really hard and squinting your eyes and hoping to spot the mistake. There are other strategies that are much more actionable and teachable than that. And so we came up with a collection of these. Here are a few that are included in our chapter that we hope act as a sort of toolkit for debugging for you and your students. And on the other hand, while we were trying to get some specificity in there, we were also careful to try to articulate them at a level that made sure they were applicable across a range of platforms and languages. So we hope it's a useful toolkit for you, wherever you are on your CS journey. If you're teaching little ones, which are in primary school, we'd like, or older students, text or block-based languages. If you're thinking about debugging for the first time, or if you're coming in looking for a fresh perspective.
Given the amount of time we've spent honing our teacher-facing voice as curriculum developers and working with teachers, and knowing that they love an immediate takeaway, we also made sure to include tips on how to create a classroom culture that supports debugging. Much has and can be said about culture in computing, but we can be sure that as teachers, we spend time and effort to explicitly or implicitly create and foster a positive culture in our classrooms, regardless of subject. For students to engage productively in debugging, it's important to be deliberate about reducing the stigma associated with making errors. Often making mistakes is positioned as oppositional to efficiency. We advocate for a transition which frames errors as productive, an inevitable and important part of the learning process. This classroom culture change is in fact crucial to the success of debugging as a practice. While students may learn specific strategies in isolation, as programs become more sophisticated, multiple types of errors may occur, requiring more than just a single strategy. Attention to the classroom culture then makes a more hospitable atmosphere or environment for these strategies to work in concert with each other. One example of how error stigma might manifest that we see a lot with young kids is the tendency for them to completely throw out their buggy code and start over, instead of re-engaging with the code they've already written. We believe that in a productive debugging culture, students may be more willing to persist in actually using the specific strategies they've learned to successfully debug their programs.
So those are our two big takeaways. As longtime friends, as collaborators, if you've probably picked up, we deeply enjoyed writing this chapter together. We want to thank Shuchi for the opportunity and this general community for being so welcoming to us as relative newbies. And we hope you enjoyed the chapter.
Thank you so much, Katie and Carla. Wonderful chapter, very useful ideas and tips. That was TU. All right. Maya and Todd are ready.
Hi, thank you so much again. We're just going to mirror everybody else's sentiment about what a wonderful opportunity it is to be part of this community and to write this chapter. My name is Maya Israel. I'm an associate professor of ed tech at the University of Florida. As part of the Creative Technology Research Lab, my co-author Todd's going to introduce himself as well.
Hey everybody, I'm Todd Lash. I am also part of CTRL, except for I am part of CTRL up north at the University of Illinois, where I'm a graduate student in the Department of Special Education and a 2020 Computer Science Teachers Association Equity Fellow.
So as you can see from this title slide, we wrote a chapter about universal design for learning in computer science education. So kind of the first question was, what will teachers get out of this? What we found is a lot of teachers who we work with have heard about universal design for learning, but they don't know how to apply it within the context of computer science education. So even if they are familiar with it in the context of math education or science education or whatnot, what does it look like in this particular context is new to them. The other part is that that we want teachers to know about, even though my background, and Todd just mentioned special education, is working with students with disabilities. The idea of universal design for learning is not about students with disabilities. It's about proactively planning for the range of diverse learners that are in your classrooms. So knowing from the get-go that all students, like whoever said CS for all, Dan said that earlier, right? We really do want to create instructional activities that don't otherize children. So whereas before we would have like, here's a lesson for the quote unquote average child, now we have to make something different for an other, whether that student needs an enrichment activity or that student needs some additional support. The idea of universal design for learning is that it's a framework that allows us to think very proactively about the range of students. So the chapter has that kind of basic UDL, how does it apply within CS education, and some examples. So I think, Todd, you're going to talk about one of those list of examples.
Yeah, so when we think about introducing our chapter and kind of think about what are some of the key takeaways, Maya kind of hinted at this, but the basic idea behind the chapter is that learner variability is the norm. And that's the way that we should approach CS education. And really that variability is a strength. There is no such thing as an average learner. So how do we design instruction that has that flexibility and is not always designed for this kind of mythical average in the middle, right? And so UDL gives us a framework by which we can do that. What you're seeing here is this is a table that we've adapted the original UDL table from the Center for Assistive and Special Technologies, CAST, that was more of a general look at UDL across multiple disciplines. This is one that we've developed specifically for computer science education. And one of the cool things about this is, and this is only a small part of it, this is a living document. And so you might see it over the course of the next year or 2 years, and it keeps growing. It's crowdsourced, so every time we do a professional development session or we do a presentation, we ask the participants to help us continue to populate this. And so again, we bring the community into developing how we can implement universal design in terms of computer science education. Let's see here. So one of the other things, a major takeaway, is we're thinking about trying to identify barriers that are present in curriculum and tools and materials that we utilize, and knowing that those barriers, the barriers are not about the kids, the barriers are about those curriculums and tools and pedagogies, right? It's how are we disabling instruction and how can we enable it by thinking about flexible frameworks like UDL.
So one of the ways that we do this is, so Todd just mentioned these 3 different universal design for learning principles, and there are a lot of ways of enacting them. But from a pedagogical perspective, we don't want teachers to just go to that crowdsourced document. We want them to think about what it is that they want to teach. And so starting off with thinking about what are my instructional goals? What do I hope the students can get out of this? And then oftentimes we then flip that in terms of student facing language. So when Carla and Katie were talking about kind of this integrated materials, we created things like I can statements out of that. And then once you have the goals, we think about what are the barriers to students achieving those goals. And then once we've really thought about that, then we can use those, these 3 universal design for learning principles to specifically think about who are the students in the classroom, what are my goals, what are the barriers, and how can I address those barriers. So the focus really is on the pedagogy and then using these 3 principles within them. And I'll just kind of end by saying that the chapters that we've heard about, these are really fantastic pedagogies. And what I would urge folks to do is to think about how might we think about inclusive practices within all of these. And so UDL is one of those frameworks to think about. So when you're talking about recursion or conditional logic or whatnot, or pair programming, there are ways to think about inclusive practices as compared to those that exclude particular children. So, so that's it. Thank you so much.
Thanks, everybody.
Thank you so much, Maya and Todd. Such a useful chapter. Phil Bagg is going to present our second chapter that we co-authored on variables.
Thank you. There are in my mind 2 types of researchers. Those who write and can be read easily by teachers, non-specialists, and those who don't. And Shuchi's work definitely falls into that can be read, can be understood by teachers. In fact, her work first came to mind when I was looking for how we could improve primary pupils' understanding of variables. And after reading some of her research, I went back into class enthused to go and try all sorts of new things, which worked really well. Couple of years on, having shared some of the research and some of the things that we did in our class together, it was lovely to be asked to just work on a chapter together. So, what's in this chapter? Well, first of all, there's quite a good technical definition of what variables are, which I think is really quite important for novice learners, because it's not actually that obvious what they are, having sat on lots of forums when people have spent a lot of time discussing it. We also think about the many ways variables can be used. And that's quite important, and really sort of try and split those into the ones that are better for novice learners and the ones that are better left a little bit later as well. We think about lots of everyday examples and ways to introduce variables outside of programming first, to reduce a pupil's cognitive load when they're understanding a difficult concept. And we think about sort of nice ways to introduce those for elementary primary pupils as well. Things like role play and writing their own everyday ones to really get a bit more of a handle on what they are. We think quite a lot about analogies. Those that are good analogies that can really grow with the learner as they progress and build on their understanding of variables, and also those analogies that can cause misconceptions later on that might be better actually avoided. We suggest a progression of complexity of things. We look also at variable range and variable assignment and naming conventions and a host of other things. And as always for this book, it's very much written in a way that is accessible for the non-specialist teacher teaching in elementary or middle school or further up. Okay, and also for those who want to get that next step of learning as well.
Thank you, Phil. It was wonderful collaborating with him. Like he said, he has used some of these ideas. So Jane, you're up next.
I again want to say thank you to Shuchi for organising the book and for having me to help author a chapter with her. I'm Jane Waite, and I'm going to do the same as Steve. I'm going to do a shout out for two of my supervisors, because I'm doing a PhD, who are here as well. So I'm going to do a shout out to Paul Curzon, who's at Queen Mary's, and also to Sue Sentence. And I wouldn't be here if it wasn't for them. So a massive, great big thank you. Before I came to do research, I was a teacher, and then before that I worked in the industry for 10 years. But what's that got to do with all this? So what are you going to get out of our chapter? Well, we've kind of got a gathering of lots of different strategies which can help scaffold learning. We've got the things that are here, everybody else has talked about. So there's code reading, worked examples, use, modify, create, so that moves into constructionism at the end, and prim. And I'm going to just talk about prim. And because we've all been sitting here listening, I think we should do something. So you really do have to see my screen now. So what I'd like you to do is we're going to do a prim. So I'd like you to predict what that code is going to do. And I'm going to just sit here quietly for 20 seconds. Go. Read the code. Right, counting down now. 10, 9, 8, 7, 6, 5, 4, 3, 2. Did you get a chance to finish? Well, you're going to have to read the book in order to find out what it does. So what we do with Prim is we get children to read the code. It's all about code comprehension, which lots of people have talked about. And then we get them to run the code. Now, in the research, this is Sue Sentence's research, and I was very fortunate to be on her team with her. That some teachers, when they got to the running situation, they whipped their class up into a frenzy in order to go, their kids are going, run, run, run. Or you can ask the children to run the code themselves. Now, I could run it, but I don't have time. But you can find out if your prediction is correct. So the children then run the code, or you run it on their behalf. And then there's a period of investigation. So it's P for predict is for the beginning of Prim, R for run, and then I for investigate. And the investigate is where we really start to get children to think about the constructs and the concepts that we're teaching them. And there's something called the block model by Carsten Schultz that can be used in order to scaffold those questions, which I would really recommend people look at because I think it's rather smashing. And then the M is for modify. So children are now starting to take responsibility for their own code. So it's not someone else's, it becomes theirs. So this draws on the use, modify, create model. And then you move into make. So we're up now, where I can do a little bit more of work that's to make it very much my own. So Prim is predict, run, investigate, modify, make, and it draws together code reading, use, modify, create, the block model, and also just using example code, and levels of abstraction as well. So the strategies that we've introduced in this chapter are code reading, live coding, worked examples, use, modify, create, and Prim. And what you get out of it are some things that you can practically do in your classroom. So no bells and whistles. I just wondered at the end if we could play Wink Murder. I've never tried it online, but do you think it would work? Anyway, I finished. Was everyone for playing Wink Murder? Would everyone just go and everyone would die? I don't know. Anyway, it's been a long hour and a half. I'll stop sharing now.
It has, Jane, and thank you for injecting your wonderful sense of humor here.
Yeah, tell us what the code does, Jane. You can't leave us leave us hanging.
I can't tell you. You've got to find out for yourself. And actually, will it disappear? That's the big question. Does it ever really disappear? Anyway, I'll leave that one with you.
Katrina shared the chapter. So thank you so much, Jane. Wonderful collaborating with you on this chapter.
It was good fun.
We're on to X. We're on to the 3 very difficult alphabets. And I want folks to try and tell me what they would have set X, Y, and Z to be. Yeah. But we had a wonderful chapter on crossing boundaries next.
Right, I think that's me. Can you see my screen? And yeah. We're delighted to share with you a brief summary of Chapter 24 of the Computer Science in K-12 book. This chapter is called Crossing Boundaries with Physical Computing, and it's by me, Sue Sentence, and my co-author, Catherine Childs. We're both from the Raspberry Pi Foundation. We'd like to share with you some of the highlights of this chapter and what we think teachers will really find useful reading it. So firstly, we outline what physical computing is, the background and the benefits. We've included this great full-page table of devices, categorised into different types of devices, with lots of examples that we think teachers would find useful. We've also got a section on tips and things that we've learned from experience, with a focus on good pedagogical practice and how to plan an effective lesson with physical computing. We've got some examples, one from secondary and one from primary, and we're going to talk about those a little bit more in a moment. And finally, we look at the barriers and the obstacles, and we thought it was really important to face these head on and acknowledge some of the obstacles, but also think about some of the solutions. And we talk about how to get your classroom really organised so that you can make the best use out of the time that you have with your students and physical computing. And finally, we have lots of signposts to resources, some further reading, and that enables teachers to look a bit further into this topic. So now Catherine's going to give us a little bit of a practical.
Thanks, Sue. One of the activities in the book chapter is to create a BBC microbit pedometer, just like this one. This uses the onboard accelerometer to detect motion. So every time the BBC microbit is moved by taking a step, 1 will be added to the step counter here. Let's simulate that now by giving it a shake. Okay, so you can see that's how it works. Every time the microbit moves, the step counter increases. The second activity in the book chapter uses a sense hat, which connects to a Raspberry Pi computer to add some functionality. We've used the temperature sensor and the humidity sensor on the sense hat to create a weather station activity. I'm demonstrating this in Trinket, where I've got some code written in Python. I'm going to run this and use a simulator of the sense hat here. We're looking for a temperature of above 30 degrees and humidity above 80%, and we should get, there we go, a warning symbol.
So that's all from Catherine and me. We really hope you enjoy reading our physical computing chapter, and we wish you all the best with your physical computing adventures.
It was wonderful, and the chapter is wonderful, and lots of connections to science and geography and other subjects. So great integration opportunities too with physical computing. Thank you so much. So I'm going to share my screen. We're on to Y. Yay, almost there. Chapter 25. So naturally it starts with Y. I don't know what people have responded to my question about what they might have chosen X, Y, and Z to be. Anyway, this chapter is basically about good habits of programming. And it takes a leaf out of an earlier work that I will talk about in just a moment, and focuses on writing readable code that helps not only the reader, the teacher, or classroom peers, but also learners themselves. And that should be one of our goals when we teach programming, writing readable code or clean code. And it shouldn't be an afterthought, that's taught later on, but because many of the ideas shared in this chapter actually help students develop a stronger foundation of coding skills, actually. So the inspiration for this chapter comes from two sources. One, you can see, is also the inspiration for the title of the chapter. It's a 1986 article by Joni and Soloway that I have loved for years. And the other is this one on Programming Pearls by John Bentley, which is kind of dated now, but I love the idea of the pragmatics of coding, which are often never taught, but so important. So this chapter actually distills, several key programming pearls, as just borrowing that phrase. And, just as examples from these articles and from Programming Pearls, the pearls, of course, are very pithy and very interesting. The last one, don't debug standing up, and many of them sort of talk about older languages or software engineering, but several are very useful for what we are teaching in K-12. So this chapter basically shares lots of do's and don'ts, around naming of variables, language constructs, modularizing code, testing and error handling, iteratively building, commenting, things that we sometimes leave out of our intentional teaching process. And there are also things to avoid: unreachable code, code duplication. Code duplication, of course, is a wonderful way to motivate the use of functions. Fine-grained and bottom-up coding that is inspired by this wonderful article by Mir Gonsalan, Mikhal Armoni, and Moti Ben-Ari from 2012, which says that, languages like Scratch and Snap, and often, the ones that sort of get kids going right away, often have this, paradigm of coding, and that can sometimes become problematic when, it's sort of in opposition with, top-down or planning before coding. Inappropriate use of conditionals and loops. But the big point that it makes here is that you want to call out these do's and don'ts, or demonstrate and model them and motivate these good habits, and make that a deliberate part of teaching introductory programming. And with that, I will turn to BT for the last chapter. Yay, we made it.
I'm really excited to be here. And I've heard that we are now doing 10-minute presentations. I prepared an extra long one to close us out.
I love it. I love it. Brilliant. Brilliant. I should have pulled that.
I wrote a chapter called Zestful Learning, and I'm excited to share some highlights. So I want to begin with a quote from one of my previous colleagues. If you construct a classroom environment that is joyful, it creates an intrinsic rewards and leads to positive feelings about CS. Students feel about CS as something that they want to continue learning and exploring. And I believe that zestful or joyful learning is both the process and the product or the outcome. And the reason it's important is it not only leads to like high engagement, but also more effective learning in computer science. And so I'm going to walk through what I've outlined in the chapter as like 6 elements that I believe contribute to zestful learning. The first is creating relevant projects. It is important for students to be able to connect with the content and create things that they actually care about. So that is drawing on their interests and things that they use. It is second about scaffolded creativity. So it's important for students to have the outlet of being able to do things that challenge their brain and allow them to explore creatively. But as other chapters have noted, that process needs to be scaffolded so that students don't fall too far down and also start on the right step. So the goal of doing this is that they arrive at similar outcomes and get the amount of support that they need for that. The third, I believe, is the importance of showcasing and having an authentic audience. So it creates a lot of purpose when there is an intentional opportunity for presenting one's work. And so I've seen teachers do this really effectively by having showcases at the end of every period or often at the end of a week or unit, and the students know that they have that opportunity and they look forward to having the opportunity to like show off to their peers as well as their community. Another element is having a supportive classroom culture, and I think that there are 2 kind of key elements here. One is like the role of the teacher as the coach, and perhaps a more supportive coach is not yelling. And the goal here is that it is figuring out what students need in the moment to push them forward on those creative projects. And again, I think that an analogy for zestful learning is closer to writer's workshop at elementary level than what is often like a college level course. It is about like them along the way, diagnose learning, and also clean up learning that happens. The second element of that is like teamwork, and it's that students learn how to foster an inclusive culture. They learn how to give appropriate feedback to solicit it, how to involve others, how to design for other audiences. A 5th element is the need for discovery and exploration. I think people, especially children, I like the child on the leash here, want to run free and to explore things. And we need to give that opportunity because that creates a lot of joy. And so I think there's a great need for tinkering and have the opportunity to like play as part of learning. Obviously that should be constrained, so maybe tethering them to the wrist. And last, I think that there needs to be physical activity. And I think this involves a couple of things. One is like all good instruction involves like not sitting and waiting. So I hope that you've gotten up during this long call because that's also important to have a little movement. So that is having different modality as well as breaks. And it's also taking a chance to like unplug and think about having more concrete representations of these concepts. So those 6 things are the elements that I've summarized as part of zestful learning. And like the others, if you want more, you can see what this excellent book is. And I will pause there.
Oh, that was fantastic, BT. And thank you for making it. I know BT's had a very challenging schedule and made it in time for this and made time to do this. So thank you so much. And for a wonderful chapter and presentation. It woke us all up. So we've been here, we've been at it for 2 hours now. I wouldn't blame anybody if they just sort of smashed the screen and ran away. But it's a wonderful wrap up of our A to Z chapters. We managed to fit it all in. And everybody presented, whether remotely or without being here today. So thank you so much. Thank you to everyone who has participated in. Thank you for all your words of appreciation. They are much appreciated. And as I said in the very beginning, it was a dream, and it was this team that made it come true. So thank you all very, very much.
I think you deserve a big applause.
So applause for everybody.